Good afternoon, ladies and gentlemen. My name is Dr. Antonis Papadakis, and I will be presenting KYAMOS Limited solutions concerning real-life simulation of compressible flows using graphical processing units and artificial intelligence. This is a work funded by the Research and Innovation Foundation and co-funded by the European Union. I am the CEO and founder of KYAMOS Limited. The summary of the project: our aim is to accurately predict compressible fluid flows and to capture shock waves. The methods to be used is the finite volume total variation diminishing method and the artificial intelligence time unit scheme. Our approach is to conduct finite volume total variation diminishing simulations, compare them with exact solution, AI train and predict the tuned simulations, and compare the AI tuned results with the finite volume PVD simulations. The finite volume total variation diminishing scheme, the so-called finite volume PVD scheme, it preserves monotonicity by making sure that the total variation of the discrete solution diminishes with time. It is used to solve hyperbolic partial differential equations and addresses undesirable oscillatory behavior of higher order schemes. Regarding the Euler equations which we solve, these are special partial differential equations, a simplified form of an Navier-Stokes equation where the viscosity and conductivity are set to 0. It can be used both for compressible and incompressible flows. The conservation form of the Euler continuity equation is as follows: 0 dt has divergence of rho u equals 0, where rho is the density, t is the time, and u is the velocity. Regarding the conservation form of the momentum equation, we have the momentum dt has divergence of rho u convoluted with u plus grad of p equals 0, where rho u is the momentum, p is the pressure, and u is the velocity. Regarding the energy of the Euler energy equation, we have E epsilon dt plus divergence of E plus P and U equals 0, where E is the energy, T is the time, P is the pressure, and U is the velocity. And to close the system of equations, we utilize the equation of state, which basically says that E equals P over gamma PR, where gamma specific ratio is equal to 1.44 in this case, and plus rho U squared over 2. Regarding the finite volume method, it performs well in compressible flow scenarios and guarantees conservation of flux. The integration in the finite volume method is based on the control volume of the unit cell, so the domain will be discretized into discrete control volumes. These control volumes each have a centroid, representing the values of the primitive variables. In this case, primitive variables will be density, velocity, pressure, and energy. The finite volume arising from the Euler equations is equal to the integral of du dt dv plus the integral of divergence of the flux dv equals 0. The flux is across the cell's unit cell surface, where v is the volume of the cell. For the limiters, we use the boundary limiter, which is a second order symmetric PVD limiter, and the HLL limiter that is specialized in solving Riemann discontinuity problems. And for the time domain, we utilize the improved Euler method, the second order method, which is used to solve ordinary differential equation given an initial value. It is called the Riemann-Rudolph method for the discretization. For the test case, we utilize the short shock tube test case, which is a well-known benchmark compressible flow test case. It's one of the few compressible problems in computational fluid dynamics where there is an ideal solution. Now, regarding the 5 discrete regions of the short shock tube problem, a short shock tube problem is basically a tube with a diaphragm in the middle. We put on the left high pressure and density, and on the right low pressure and density, and then we break the diaphragm, and then we have propagation of shocks within the tube. Number 1 is the undisturbed left ambient region, the initial high pressure region of the compressible gas that is not affected by the shock wave or expansion fan wave. Number 2, moving towards the right, is the shock left region. This region resides between the shock wave and the contact discontinuity, where the gas is compressed by the advancing shock wave. Number 3, it's the contact discontinuity. It's a thin region separating the shock left and right gas sides. In the case of pressure and velocity, the profile is continuous, so we don't exhibit any discontinuity, whereas the density usually exhibits discontinuity behavior. Number 4, on the right, is the shock right region, the region between the contact discontinuity and the head of the expansion fan, where the gas has been accelerated and reacted by the expansion fan. And finally, on the outer right is the undisturbed right ambient region, where the initial high pressure region of the rather the compressible gas is not affected by the shock wave or the expansion conversion. Now here we see the two-dimensional results from the finite volume TVD simulations. First of all, we see the density, pressure, and velocity with regards to the x and y coordinates. One thing to note is that the simulations in the right calculate on both density, pressure, and velocity are constant, which gives us confidence that the results are correct. Along the x direction, we can see that the density produces this extra shock along the contact viscosity gradient, which is not the case in the pressure and the velocity. Another thing to note is that the form of the waves are all correct, and which gives us confidence that it gives the right results. But to ensure 100%, we plot the one-dimensional results of the finite volume simulations in red, and we compare them with the exact solution in blue of the short shock tube. As you can see on the left, we have the density, on the middle the pressure, and on the right the velocity. We can see that there is a very close agreement between analytical and predicted results. The only differences we observe is around shocks and contact viscosities, as we expected. We also see that the pressure and velocity do not show so much difference when compared to the density simulation. And here we can see a two-dimensional propagation of the velocity, starting from the middle where the diaphragm has broken. And we see the wave moving towards left and right, with the velocity building up at around 0.9 meters per second, which is in agreement with the analytical solution of the shock tube. Regarding the artificial intelligence, specifically UNET that we have utilized, it's an image segmentation technique. It segments and extracts important macroscopic features from 2D and 3D simulations, for example, from speed, pressures, temperatures, energy, and velocities. It has the ability to handle small data sets and multi-class segmentation problems. It partitions the image into multiple segments, with each segment corresponding to a different region of the image. It deals with small training data sets by using data augmentation that involves applying various image transformations to the input image and the corresponding segmentation tasks. The unit is based on solely on convolutional neural networks. It consists of an encoder-decoder architecture, and it is able to handle large and complex data sets. It is flexible in handling multi-class segmentation problems. It is fully based on convolutional principles, avoiding fully connected layers, and the utilization of steep connections enable it to learn robust features and the segmentation boundary based on detailed information from the input image. Now, UNET can capture effectively complex flows and heat transfer phenomena by handling large and complex data sets, while at the same time handling multi-class segmentation problems. It is an ideal choice for CLD analyzing marginal phenomena, and it can capture and predict the results of fluid flows, higher density velocity pressures, with the emanating error being acceptable for fluid flow simulations. Now, in this work, we have had a breakthrough. We proposed something unique and innovative, the TUNET, which is basically a time version of the UNET, by adding a time variable as input. And we have seen that the time sequence of events was well captured. We have conducted 100 simulations with 50 time steps for each variable, so 5,000 files for each input and each output variable. And since we have a total of 3 inputs and 3 output variables, which means 6 variables times 5,000, we utilize 30,000 files. The parameter that was used to then teach the model was the learning rate was 0.001, the batch size was 64, the epochs we used in one case 100 and 1,000, and the filters were 316, 50 to do and so on. Now, here we see the results, which compare the finite volume TVD results with the unit results in the first two columns, and on the rightmost column, we see the error. In the first row, we see the density predicted by the finite volume TVD scheme, and here we see the predicted by the TUNET, and here we can see the error. And we see that there is a very close agreement between the results. The TUNET can capture both the shocks, the formation, and the error is very small, on the order of 0.16 maximum, close to the right shock. Results are very similar for the velocity. Results are very close to each other. And again, we have errors of the order of 0.17 maximum, close to the shock on the right. For the pressure, it's a bit different. Again, we have an agreement between both the final volume TDD and the lunar tune of the predicted result, but we see that the error is much smaller, of 0.06, then it is more PCB. So we have seen here that the tuner is able to capture satisfactorily the prediction of finite volume TDD result with the time included. So this innovative finite volume TDD scheme and the AI tuner we propose, they produce very similar results. The error between the expected and predicted results is calculated to be very relatively small. And then the work should be conducted in investigating the effects of different parameters, such as the learning rate, batch size, number of filters, the number of data sets, and the number of inputs. Thank you very much. If you have any questions, you can post them